thank you for the introduction, and so thank you to Claire for organizing this conference and for inviting me to speak in it. So I will start with two classical isomorphisms. So consider a quadratic surface in P3. So everything is over C. And so quadratic surface, general quadratic surface. So the important thing here is that it contains no lines. And then Bouvier remarked that there is an involution on the Hilbert square of S. So usually it's written like this, or Hilbert 2 of S, which takes 2 points. So let's say PQ, P plus Q, or PQ, I don't know. And so it's a self-map of this square. It takes 2 points so the residual intersection of S with the line PQ. Okay, so you take 2 points, you have S here, you take 2 points, and so they're on the line. And the other 2 points of intersection, this is, let's say, sigma of PQ. Okay, and so this is so as we have learned in talks the other days, this is a Hyperkähler fourfold. And so this involution is anti-symplectic, and its fixed locus is the set of is the surface of bitangent lines to the quadratic. Okay, so this is my first example. The second example is also due to Beauville and Donaghy, and was mentioned probably several times in the other talks. So I won't give the definition, but if you take S, a general K3 surface. So this is a general K3 surface of degree 4. If you take a general K3 surface of degree 14, then there's a beautiful geometric construction which shows that the Hilbert square of S is actually isomorphic to the surface of lines. It's not the surface. So to the fourfold of lines, so this is a set of lines contained in a Pfaffian cubic fourfold. So here I need also that S is general, same as in here. So in this case, W will be a general, so this is a general cubic fourfold of discriminant (14). So this is the special in the sense of a Hassett. So it belongs to the divisor CD, which was mentioned by Gabi Farkas on Monday, I think. Okay. So I'll avoid to say special, because then I'll have to say a general special cubic fourfold, which is not very nice. So the aim of my talk, so this is what I consider unexpected isomorphisms, and the aim of my talk is to present several examples of this situation. And so the main tool for producing these isomorphisms is a Torelli theorem for Hyperkähler. So Torelli theorem for, so I'll stick to Hyperkähler, so HK, fourfolds, which are deformations of Hilbert squares of K3 surfaces. So usually they're called of K3 2 type. So this theorem is in the form that I'll present is due to Verbitsky and Markman. Verbitsky, Markman. 1N, I think. And he says the following. So, maybe I'll write for Janusz. I'll stay at the top of the blackboard. So let's say you have two such Hyperkähler fourfolds, so two such meaning Hyperkähler fourfolds of K3 square type, and so with polarizations, H1 and H2. And assume there is an isometry. Okay, so assume that there is an isometry of Hodge structures. Assume that there is an isometry. So between H2 of F1Z and H2 of F2Z, phi of Hodge structures such that, which takes the one polarization to the other, so such that phi upper star, phi of H1 is equal to H2, then there's an isomorphism U between F2 and F1 such that phi is equal to U upper star. Okay, so this is an isomorphism of Hodge structures. It's also an isometry for the Beauville-Bogomolov Fujiki forms on these lattices here. Okay, so this is the best Théorie theorem that you can hope for, and it's not. You have to be a little bit careful with this kind of statement for Hyperkähler manifolds, but in this case, this is the only one that we'll need. It is true. So this is one tool. The other tool will be a description of the ample cones. So description of ample and movable cones, but especially ample movable cones for general help 2 of S. So here S will be a general K3. So let's say SFS is a general polarized K3 of degree 2e. So I guess that's in Gabi's terminology, or is it not his, but classical terminology is genus E plus 1, I guess. Okay, then maybe I should say very general in the sense that I assume that the Picard group of S is generated by the polarization. So Fs here is a polarization of degree 2e, which means that Fs squared is equal to 2e. Then the Picard group of the Hilbert square is isomorphic to Zf plus Z delta. So F is the Neff and big line bundle on the Hilbert square that's defined, that comes from the polarization on S, and delta is the half of the class of the diagonal. We've seen that several times in this conference. And so the intersection form here for the Beauville-Bogomolov-Fujiki form is the intersection matrix, is 2e00 minus 2. Okay, so F, as I said, is Neff and big. So let's say in this, in the real vector space generated by these two classes, R plus F is an extreme array of both of the Neff cone, of both the Neff cone, Neff of S2, and the movable cone. Okay, which is the set of classes of divisors such that some multiple defines a linear system which has no fixed part of codimension 1. Okay, so so once I have this set up, it is now known what the so the other extreme arrays of these two cones have the so I'll define two numbers. So the other extreme array of, so let's say the Neff cone. So let's say it's the cone generated by the class of F plus some other class, which I'll write as F minus nu S delta. Okay, so nu S is a positive number. And the movable cone so same thing here, I'll just write mu S. Okay, so mu is greater than or equal to nu. Okay, so it's an easy situation. You're in a plane, so the cones are very simple. So the theorem, which is due to it's a much more general theorem, but in this case, the theorem due to Bayer, sorry? They have more results, yeah, okay. So they have, I believe, a general description, but I'll only use the, so it's Bayer and McCree. Which description? Well, I don't have any statement at the moment, so. No, it's just a definition. I define two numbers like this. The Picard.
It's always assuming A of S.
I'm assuming that the Picard number of the Hilbert square is 2, so in this case the cone is just a plain cone. No, sorry. This is just a notation. And the theorem will tell you what these numbers are. Okay, so situation as above. So actually, I need to set up one more piece of notation. So this theorem will answer a conjecture of Hassett and Schinkel in this case. And so it is very important to know whether there are classes of square -2 and -10. Okay? So in other words, we want to, if you look at the intersection matrix here, you want to look at the equation which is, so let me put it in the right, A2 minus B2E is equal to T. Okay? So it's a sort of a Pell type equation, although I learned from Wikipedia that Pell has nothing to do with it, but anyway, his name is still attached to it. So here E and T are everybody's an integer here, E and T are given, and A and B are integers. And so I call this equation P E of T. Okay, so P is for Pell. Okay, so this has a solution if and only if minus 2t is represented by this Bovil-Bogomolov-Zhiki form on this Hilbert square. Okay? So I'll use this notation to simplify the statement. Okay, so there are two cases. So if the equation P4E of 5 has no solution, so in other words, minus 10, I mean, apart from this 4E, but minus 10 is not represented, then two cases, either E is a perfect square. So if, moreover, E is a perfect square, okay, so sorry, maybe I'll add something here. So the theorem is that the numbers we have, so US, they only depend on E, US and US, where I'll define nu E and nu E in the theorem. Okay? So if E is a perfect square, the two cones are equal, and the other slope is the square root of E. If E is not a perfect square, then we have, they are still equal, but they're equal to E B1 over A1, where A1 B1 is the minimal solution of the equation P of 1. So this is what is usually called the Pell equation, and this one always has a solution. Okay, when you set that equal to 1, and the minimal solution is the solution for which A1 and B1 are both positive and smallest possible. Okay, and so the last case is if this equation has a solution, let's say A5, B5, so which I assume to be minimal. Then, so, okay, so case A, B, and so this is C. So then the two cones are different, and so nu E is equal to 2E B5 over A5, and it's smaller than mu E, which is still equal to E B1 over A1. Okay. So in some sense, I mean, maybe it's not very obvious what this theorem means, but it means that to be nef, you have to have a non-negative intersection with all -2 classes. Okay, so it's easier to say it this way. But in terms of numbers, this is what it is. Okay, and so there's actually one can describe. So if you look at the nef cone, its orthogonal is the cone of the Murray cone of curves, and so these two extremal rays correspond to two extremal rays of the cone of curves, and they can be contracted. And so the first contraction, which corresponds to the dual to this F here, so one contraction is just the Hilbert to Chow morphism. And the other contraction can also be described. So the contraction of the other ray okay, sure. Yes. Much more is true, actually. They have a general description. So the other contraction, so it depends on the three cases. So I'll be quick here. So in A, it's the Lagrangian fibration. In case B, it's a divisorial contraction. And in case C, it's a small contraction. Actually, in case B, you can be more precise. If I remember correctly, it says that it is also of this type here, okay, for another K3 surface T. Okay, so it looks like this. S2 is isomorphic non-trivially to the Hilbert square of another K3, and this is the Hilbert to Chaire morphism. Okay, so everything here is due to Bayer and Macri. Okay, so sorry for this very long theorem, but it has nice applications, and the first application was given by Voisin, Cataneo, Nieper, Wiskirchen, and Sarti to the automorphisms of these Hilbert squares. So again, here and in the rest of my talk, S will be a very general polarized K3 surface of this type. Okay. So how can you use this description to identify the group of automorphisms? Well, I think it was mentioned maybe by Serge or someone else. So of course you can act, so there is an action of the automorphism group on the neuron server group, which here I wrote as PIC, but it's the same. Okay. And this map is actually injective almost always. Okay, so anyway, there's a map like this. There's also a map from the birational, this was mentioned by Serge, this I'm sure, of the birational automorphism group of S of the Hilbert square. Oh, okay, so I'm sorry, I'm going too fast here. Of course, the image of a Neff line bundle baryon automorphism is still Neff. Okay, so it preserves the Neff cone. Any birational automorphism also acts on PIC, and this is because this is a Calabi-Yau manifold, as Serge explained. And this time it preserves the movable cone. Okay. So then, since this cone is very explicit, it's not too difficult to analyze what kind of isometries you can have here. So, sorry, move. Thank you. I should say also that obviously the kernel, if you are in the kernel of this map, then you fix any ample class. So you are actually an automorphism. So the kernel of this map here is contained in the automorphism group. Okay. So this allowed people I mentioned earlier, Boissier et al., to identify what the automorphism group of a Hilbert square of a very general polarized K3 is. And so let me state their theorem. So Boissier, Cataneo, Nieper, Wiskirchen, and Sarti. So a situation as above. Then the automorphism group of S2 is non-trivial if and only if the Pell equation PE of -1 has a solution, but P4E of 5 does not.
I guess one trivial just means being equal to Z mod 2 or something.
Wait. Yes. The only non-trivial automorphism is then an anti-symplectic involution. And so, I mean, you can describe everything. It acts on this. You can describe its action on the Picard group. Okay. So in some sense, so this is a generalization of my first example where so E was equal to 2. So degree 4. So this is the Beauville involution. And so I believe that there is no, so the next case is, I mean, it's easy to, there are even websites where you can solve all these equations. You plug in the numbers and it tells you yes or no. I guess you can do it yourself if you're good enough. But so the next case where these two conditions are realized is when E, let me write down some numbers. So actually, when E is equal to m squared plus 1, and m is at least 3, then obviously the first condition is real. I mean, both conditions are realized. This one is obvious. The solution is m and 1, or 2m plus 1 and 1. And so this gives you values 17, 26, 50, 56, etc. And so when okay, so okay, why did I put m greater than or equal to 3? It's because when E is equal to 5, so obviously the PE of -1 has a solution, but also P4E of 5. Okay? So in this case, there is actually a birational evolution. So we're talking here about K3 surfaces of degree 10, and it's something which is known, which can be geometrically described, but I'll come back to that later. When E is equal to, so when m is equal to 1, this is the Beauville evolution. When E is equal, I mean, for the other values of E, there is no geometric description of this involution. Okay. So there are many, of course, this is just one example where, I mean, the involution is really produced via the Théorie theorem. Okay, so you don't have any idea what it looks like. There are many other instances where you can use this Théorie theorem to produce isomorphisms.
So this corresponds to a case B there?
Sorry?
This series of numbers correspond to the case B?
Yes. Okay. So what happens is that the involution sigma interchanges the two extremal rays. Okay. So the two contractions are, yeah, thank you, just this one. So the Hilbert to Chow morphism and the composition with the involution. Okay, so these are the two contractions. So they're both divisorial.
So it's the same K3 or?
In this case, it's the same K3, yeah.
So yes, so these must be double without such things.
Shh.
Okay,
It will come later.
okay.
Yes, of course. Okay, so now let me talk about special. I said I would not use this word, but so I'll put it between quotes. Cubic fourfold. So situation it gets more complicated. I mean, the original Hassett-Schinkel conjecture for the description of this Neff cone is actually wrong for Sn. So, but they have a modified version, and yeah, I mean they can, yeah, but it's yeah, it's a bit more complicated. Actually, I haven't looked at it. Okay, so special cubic fourfolds were described by Gaby. So let me just recall very quickly what we do. So we take my cubic fourfolds, I call them W. Smooth cubic hypersurface. And so if you look at the, when V is very general, there are not many algebraic cycles, so in the sense that the intersection of the integral part and the H22 is just generated by the square of the hyperplane class. So Hassett studied the next case where this intersection has rank 2. So more precisely, we want this intersection to contain a lattice KD, which has rank 2, discriminant D, and saturated. Okay, so this is what Gaby described, and so these these cubics form a divisor in the moduli space of all cubics, which is, I mean, they form a divisor if and only, so you need some condition on D, so you need D to be congruent to 0 or 2, mod 6, and D at least 8. Okay, so the question I want to answer here is when is f of W, which is the fourfold of lines contained in W, isomorphic to a Hilbert square. So in other words, I want to generalize the Beauville-Donaghy isomorphism that I explained at the beginning. Okay. So more specifically here, I want this isomorphism to hold for, so let's say S is general or very general. I mean with Picard number 1 of a certain degree. To E. And here also I want W to be general in this Hassett divisor. Yes, okay, so the first condition was spelled out by Hassett and also mentioned by Gaby. It says that, okay, so let me try to get this straight. So we are using here the Beauville-Donaghy isomorphism, which says that H2 of FW of Z is isomorphic to H4 of WZ. So this is an isomorphism of hot structures, and it restricts on the primitive part to isometry for the intersection product here and the Beauville-Bogomolov-Zhiki form on the other side. Okay? So if you assume that you have this, you see that, so Okay, let me try not to confuse you. So what we want to look at is the orthogonal of this lattice KD, okay? And so you see that this orthogonal should sit in, of course, H4 of WZ, so also in this here, but also in the cohomology of the K3 surface. So that gives you some necessary conditions on D, okay, which are stronger than this. Okay, but let's look at it in just a simpler way. So assume that you have an isomorphism like this. So f of W is of course contained in the Grassmannian of lines in P5. So it has a precuporization. Okay, and so its square for the Beauville-Bogomolov-Fujiki form is 6. If this is isomorphic to S square, you can write it as in the H2 of S square. So we can write it as 2BF minus A delta. So a priori, why is this first coefficient even? It's because the divisibility of G is 2. Okay, G is, if you intersect G with anything else, it has to be even. Okay, so this is always true for this factor here, so this term here needs to be even. So if you compute G square, you find that you have this equation, so it's again a Pell-type equation. But also you want G to be ample, so you want the slope here, A over 2B, to be smaller than nu E. Okay? So these are necessary conditions, and they turn out to be sufficient. So theorem. Okay, so let's choose E at least 2. And assume that this equation, which is P4E of minus 3, so if this equation has a solution, has a positive solution, AB, such that, so A over 2B is smaller than nu E, then so then the answer is yes, meaning that if you take, I don't want to write it down, it will take too long, but if you take a very general K3 surface of degree 2E, then it will be isomorphic to the scheme of lines contained in a very general cubic fourfold of discriminant 2E. Okay? So let me just write it like this. So this is a very, I mean, it's a natural condition if you look at it this way, but if you work out the numbers, it's sort of a, I mean, apart from solving the equations, you have no way to tell whether this inequality will be true, except, so in particular, so there is one way to ensure that this equation is, has a solution. You impose B is equal to 1, okay? And then you have 4E is equal to A squared plus 3. A needs to be odd, and so you write A as 2m plus 1, and you find that E is equal to m squared plus m plus 1. So then the solution is 2m plus 1, if I'm not wrong. And so it turns out that in this case, this condition is always satisfied. Okay. So you can, this is really an infinite series of examples, and this was actually proved by Hassett in his thesis. When m is equal to 3, this is the degree 13, so genus 14 case that Gabi talked about. Okay, so which is a very interesting case, actually. Yes. Let's say that it is stronger. I mean, because basically Hassett's condition for the existence of an associated K3 is just that, if I'm not mistaken, it's just that -3 is a square modulo for E.
I think Hassett's condition, I think, is saying that f of W is the relation to a more or less base of sheaves of a certain K3, and that's a certain K3. I think it's weaker.
I think Hassett's condition is just -3 is a square. And then using quadratic reciprocity, you translate it into a more effective condition on E, but this is really what it says here. So
What is D in terms of?
So D is always 2E, yeah.
D is a discriminant of the.
Yeah, so D is 2E, yeah.
Okay.
Yeah. Yeah, somehow, yeah. Yeah, if you have an isomorphism like this, I mean, it has to be 2E, the discriminant, you have no choice. So, but apart from Hassett's series, there are other cases where you can apply the theorem, which are for which the okay. So so there are other cases. For example, when E is equal to 19. No, E is equal to 19 is I have my table here. Yeah, when E is equal to 19, there is a, okay, so everything can happen. So when E is equal to 19, this equation has a solution, but it does not satisfy this. Okay. There might be also several solutions. When actually E is equal to 13, there are two solutions, A, B, satisfying the equation, the inequality A over 2B. But this is not surprising because, so this case here is the case where everything, you have everything. And so in particular, it also has a non-trivial involution according to the first theorem. So what happened is that, again, you have these two, so you have one isomorphism, but you also have the, so this corresponding to one pair, you also have another, which is just a composition with this non-trivial involution. And this explains, I mean, these two solutions are images one of another by this involution. Yeah, yes, this is the very nice case. I mean, no, I don't think we know. No, I mean, apart from the Beauville involution, I don't think these involutions have been described. But so what else? Yeah, so I was about to say that there are also cases. Yes. When E is equal to 129, then there are this is yeah, I agree. This is not likely that we'll ever do anything with this. But still, this is a case where the theorem applies, but it's not in Hassett's series. So the minimal solution is like this. Yes. Okay. So actually, I forgot to say something. Yep.
Do you have an example where you only have birational and you don't need to do a flow?
No, actually, so yeah, so this is something which I forgot to mention at the beginning, and I should because Serge is here. So using the description of the movable cone, it's not difficult to see that the birational automorphisms. So let me go back a little bit. So the birational automorphism group of S2 is not very interesting. So it's either trivial or a birational involution. Sorry? Let me put it like this, but no, I don't think so, no. But if you look at the this other Hyperkähler fourfold, this can be much more interesting. Okay? So there's an example which was done, a very beautiful geometric example done by Hassett and Schinkel, where they prove that this is the free product of Z2 with itself. And this is when degree some number 12, so E is equal to 6. Okay, so I haven't looked at birational isomorphisms between these two guys, for example, something that one can do with the, since we know the movable cone. Okay, so let me.
There's also complete description for when the final is birational to symmetric.
Say that again.
There's a numeric condition for the cases when the final is birational to Hilbert's.
Is this a question?
No, I'm telling you.
You have done that, no? Or
This is Eddington. Eddington has, I mean, it's a bit like your condition, E equals n squared, but changed by a square in front of E. So whenever E times a square is this form, then the final is birational to Hilbert's.
Is it a necessary and sufficient condition?
This is loaded. Yeah.
Okay. Okay.
So in this example, the lattice has rank 2 also?
Yeah, all the lattices have rank 2, but the movable cone may have irrational slopes.
Of course, then it's an F-cone also.
Yeah, yeah. Yeah, I should mention that there are also a theorem of Ogiso which says that whenever the Neff cone has irrational slopes, then the automorphism group is equal to the birational automorphism group, and they're both infinite. Okay. And you can give a description in this situation. So let me finish with the other kind of Hyperkähler fourfold that I like. Since Kieran is here, also I have to talk about double EPW sextics, right? So I won't go into too many details. So this is another family for which geometric description, another family of polarized Hyperkähler fourfold for which a geometric description of the general member is available. So let me just say that they have so this is my notation for double EPW sextics. So they, as the name indicates, double covers of sextics, which are called EPW sextics. So this is singular along a surface, and this double cover is ramified along this surface. So this is a Hyperkähler fourfold when it is smooth, and it has a polarization which I'll denote by H tilde, which is just the pullback of the polarization of on P5, and its square is 2. Okay, so I don't have time to explain that, but there is a relation between, there was a relation between cubic fourfolds and this the space of lines in here. There is also a very a tight relationship between these double EPW sextics and a certain kind of a Fano fourfold, which is the same kind of Beauville-Donaghy isomorphisms that I explained earlier. But I actually don't really need to introduce them, I think, except that, so we can define in the same way special EPW sextics or double EPW sextics. So in other words, for if you take in the very general situation, all the Picard group here will have rank 1, so it won't be very interesting for our purposes. But along a countable union of divisors, you will have a Picard group of rank 2. So you also get an infinite series of divisors which are labeled by some kind of discriminant. So let me denote them maybe D. So these are hypersurfaces, so parametrized by hypersurfaces in the modernized space. And so here the condition that you need is D congruent to 0 to 4 mod 8. And D at least 10, so it's very similar to what Hassett did in the cubic case. And so again, you can ask when is this a double EPW sextic a Hilbert square? So same procedure. You write the polarization as a. So I don't need to do all the details, but I mean it's exactly the same thing. You write the polarization like this, and then you express the fact that it is of square 2. So you obtain what is usually called a negative Pell equation, and the theorem is the same. So same situation as above. We assume that E is at least 3 if this negative Pell equation has a solution AB such that A over B is smaller than nu E, the Neff slope, then again, so this should be understood as it was understood before, between very general members of each family. So a very general EPW, double EPW sextic of discriminant 2E, so D is equal to 2E, of discriminant 2E is isomorphic to a Hilbert square. And now if you remember the first theorem about automorphisms of Hilbert squares of K3s, this is exactly, how should I say? I don't remember it, so I don't know why you should, but you see the point is that these double EPW sextics have an involution, okay? Because this is a double cover, so there is an involution here, okay? And okay, so let me just make sure. Okay, so it's not exactly the same hypothesis. Remember that the hypothesis was that this has a solution, but another equation doesn't have a solution. Well, they turn out to be equivalent. Okay? So this is exactly the same. So this is exactly equivalent to saying that S, this Hilbert square, has a non-trivial involution. So in other words, the non-trivial Hilbert squares that have an involution are exactly the double EPW sextic. So the quotient by the involution is just the EPW sextic. So then you might say, well, this doesn't fit so well with the Beauville involution. And so this is why here we're assuming that E is at least 3. It's almost, I think Gabi mentioned that, or no, Kieran mentioned it, sorry. In the case of the Beauville involution, so remember, it takes 2 points in a quartic and associate the residual 2 points. And then I said that there's a map from this square to the Grassmannian of lines in P3. Okay? And so, of course, it factors through the quotient by the involution. So this is 2 to 1, this is 3 to 1. So in some sense, this is saying that, so according to the theorem, the quotient should be a EPW sextic. Okay, so but the way to look at it is to say that 3 times this Grassmannian is actually an EPW sextic. Okay, so this is the case where E is equal to 2. So the theorem does not work as such, but it's sort of it's not too far from the same kind of statement. Okay. So I guess I'll stop here. Thank you.